everyone and welcome back to the Exam Ignite YouTube channel. So today we are starting with the module 5 part 2 video. If you have not watched the part 1 video, do watch it first and come back to this part 2 video. The link is in the description box. So please do watch. This is a handwritten notes which is easy to understand. I have referred the textbook, model question paper 1 and 2 and Jan 2025 and July 2024 question papers. And it is prepared in oriented that you can write the answers on listening to this notes. So please do watch till the end and let's get started now. Noise. Noise is what? It is an electronic signal that is a mixture of random frequencies at many amplitudes that gets added to the radio information signal as it is transmitted from one place to another or as it proceeds. So noise that occurs in the transmitting digital data cause bit errors and can result in the information being garbled or lost. So first thing here in this noise part, the question will be asked like write a short note on. You will be having three sub questions. One is signal to noise ratio, external noise and internal noise. So first, if they ask you to write in the signal to noise ratio, then signal to noise ratio, it is also known as SNR. It indicates the relative strength of the signal and noise in the communication system. The stronger the signal and weaker the noise, the higher will be the SNR ratio. If the signal is weak and noise is strong, then the SNR ratio will be low, and the reception will be unreliable. So signals can be expressed in terms of voltage and power. That is S by N is equal to Vs by Vn, or you can say S by N is equal to Ps by Pn in terms of power, where our Vs is a signal voltage, Vn is a noise voltage, Ps is a signal power and Pn is a noise power. S by N values can be converted to decibels as voltage is equal to decibels is equal to 20 log S by N, power is in the decibels is 10 log S by N. Next is external noise. External noise comes from the sources over which we have a little or no control. That is, we are having industrial noise, atmospheric noise, space noise. Three types of external noise. Noise that shows up as a random or voltage and can be seen on an oscilloscope. In general, noise contains all the frequencies and varying randomly. This is also known as the white noise. So there is no way to eliminate these noises. The key to reliable communication then is simply to generate the signals at a high enough power to overcome this external noise. So in some cases, shielding sensitive circuits in the metallic enclosures can aid to control. Only one thing is you can do this, metallic enclosures. Next comes the industrial noise. So firstly, it is produced by the manufactured equipments like automotive ignition systems or electric motors, generators. So any electrical equipment that causes a high voltage or a current to be switched produces a transients that creates the noise. So fluorescent and other forms of gas-filled lights are another common source of the industrial noise. Second one is atmospheric noise. It is often referred to as static, and it is usually comes from the lightning or some electric discharges that occur between the clouds or between the earth and the cloud. So atmospheric noise has its greatest impact on the signals at the frequency below 30 megahertz. Next is extraterrestrial noise. This is a solar or the cosmic that comes from the sources in the space. So one of the primary source of this extraterrestrial noise is the sun, which radiates a wide range of signals in the broad noise spectrum. Sun has a repeatable 2-year noise cycle. So during the peaks of the cycle, it makes many frequencies unstable for the communication. Noise generated in the stars outside the solar system is generally known as the cosmic noise. Next comes internal noise. So electronic components in the receiver, such as the resistors, diodes, transistors, these are the major sources of the internal noise. It infers many with weak signals. The main source of the internal noise in the receiver are the thermal noise, semiconductor noise, and the intermodulation noise. Here we are having three types: 1, 2, and this is 3. So first thermal noise. So the random motion of the free electrons. The random motion of the free electrons in a conductor happens due to the heat. So since these components are the conductors, the movement of this electron constitute a current flow that causes a small voltage to produce across the component. Thermal ignition is often referred to as a white noise or Johnson noise. Just as a white light contains all the other light frequencies, white noise contains all the other frequencies randomly occurring in the random amplitude. So theoretically, white noise has an infinite bandwidth. The amount of open circuit noise voltage appearing across a resistor or an input impedance to a receiver can be calculated using the Johnson's formula, that is Vn is equal to 4 kV square root of 4 kTBR, where my Vn is the RMS noise voltage, K is a Boltzmann constant, that is 1.38 into 10 power minus 23 joules per Kelvin. Temperature is T and bandwidth is B. R is for resistance in ohm. So this formula is required if they ask you any problem. So do remember this formula. The resistor is here acting as an voltage generator with an internal noise equal to the resistor value. See here you have a problem. You can refer this and just substitute the given values to the formula. You will get the final answer. So in many cases, the value of the resistance and the bandwidth cannot be changed. The temperature in some extent is controllable. Anything that can be done to cool the circuits will greatly reduce the noise. So heat sinks and cooling fans and good ventilation can help in lowering this type of noise. Thermal noise can also be calculated by the power level. So we are having Johnson's formula is then changed as Pn is equal to KTB, where Pn is an average noise power in watts. So for that also I have a problem here. Please do go pause the video and go through the problem. Next is semiconductor noise. Semiconductor noise, electronic components such as diodes and transistors are the major contributor of this noise. In addition to the thermal noise, semiconductor noise produce a short noise and transmit noise and flicker noise. These are the subdivisions in the semiconductor noise. The most common type of the semiconductor noise is the short noise that is produced by a random movement of electrons or the holes in the p-n junction. Some types of discontinuities in the device is a reason for this random movement of the change carriers. For example, interference between a copper lead and the semiconductor material forms the discontinuity that causes the random movement of the current carriers. Short noise is also called as white noise, in that it contains all the frequencies and amplitudes over a wide range. So the amount of short noise is directly proportional to the DC bias flowing in a device. So the RMS noise in a device IN is calculated by this formula, where Q is the charge of electron, I is direct current, and B is bandwidth. So I have also mentioned an example problem, refer that. Another kind of noise is our transistor noise, that is also called transist time noise. This term transist time refers how long it takes for a current carrier such as an hole or an electron to move from an input to output. So at the lower frequencies, this time is negligible. But when the frequencies of the operation is high, problems can occur. So transmit time noise shows up as a kind of random variation of the current carriers within a device occurring near um, cutoff frequency. A third type of semiconductor noise is our flicker noise, or you can say excess noise. This occurs in the resistors and conductors. This disturbance is due to the result of minute random variations in the resistance in the semiconductor material. This is directly proportional to the current and the temperature. However, it is inversely proportional to the frequency, and for the reason it is sometimes referred to as an 1 by F noise. It is also called as pink noise. This is our noise voltage variations in the transistor. You can observe this is our 1 by F noise, that is pink noise, or you can say transist time noise. This is my thermal noise and this is a transist noise. So here this is a noise voltage across frequency graph. Next is intermodulation distortion. Here, it results from the formation of a new signals and harmonics caused by the circuit non-linearities. Circuit can be perfectly linear, and if basis voltages are incorrect in an amplifier or it is driven into a clipping, it is likely to be more non-linear than intended. Any frequencies in the circuit mixed together forming a sum and the difference frequencies. Expressing the noise levels, the noise quality of the receiver can be expressed in terms of what noise figure, noise factor, noise temperature, and cyanide. Here the noise, these are formulas are important. The noise factor and noise figure. The noise factor is what? It is the ratio of signal to noise power at the input to the signal to noise power at the output. So S by N input to the S by N output. When the noise factor is expressed in the decibels, it is called as noise figure. So NF is noise figure. It is given by 10 log of NR. Noise figure of 0 decibel is not attainable in the practice. So the lower the noise figure, the better the amplifier or the receiver. Noise figures of less than 2 decibels are excellent. So here I have given a problem on that. Pause the video and do work on that. Noise temperature, the most noise produced in the device is a thermal noise which is directly proportional to the temperature. Therefore, the another way to express the noise in an amplifier or in a receiver is in terms of a noise temperature, that is Tn. Noise temperature is expressed in kelvins. So Kelvin to temperature scale, you should know the relation. So Tk is Tc plus 273. So the relationship between the noise temperature and the noise ratio is noise N is equal to 290 of Nr minus 1. Based on that, you can solve this problem. So next is the last topic, and the important one is the noise in the cascaded stages. So the formula that is used to calculate the overall noise performance of a receiver or a multi-stages or a RF amplifier, it is called as an Friis formula, which is given by NR is equal to NR1, NR2 minus 1 divided by A1, NR3 minus 1 divided by A1 plus A1 into A2 till NRN minus 1 divided by product of A1, A2 till AN minus 1. You can observe here, this will be my A1, first one, NR. Here this will be NR, next one, and A2, A3. Say it goes on like this. We give a signal input here, we get the output here. So where my NR is what? Noise ratio. NR1 is a noise ratio of the input or the first amplifier to the receive the signal. So next NR2 is a noise ratio at the second amplifier. NR3 is a noise ratio at the third amplifier, and so on. A1 and A2 and A3, these are all the power gains of that amplifier. So first amplifier, second amplifier, and third amplifier. This is what shown in that diagram. Note that the noise ratio, it is used rather than the noise figure, and so gains are given in power ratios rather than in decimals. So this completes our module 5 part 2. So if you have not watched the other videos, module 1 to 5 are then uploaded in the channel or in the playlist. Go through all the module videos and prepare well for your exam. I will be uploading the important questions also. Please go through that and work on these topics so that you score a good marks in this. So thank you for watching. Do like, share, and subscribe, and see you in the next video. Thank you.